Upon completion of this lesson, the student should be able to identify threat tactics and methodologies, monitor and report on validated threat activities, report intelligence-derived significant network events and intrusions, determine tactics, techniques, and procedures for intrusion sets. Upon completion of this lesson, the student should be able to identify threat tactics and methodologies, monitor and report on validated threat activities, report intelligence-derived significant network events and intrusions, determine tactics, techniques, and procedures for intrusion sets. Here are ICS protocols and security considerations. Timeliness and performance requirements. ICS are generally time critical with a criterion for acceptable levels of delay and jitter dictated by the individual installation. Availability requirements. Many ICS processes are continuous in nature. Unexpected outages of systems that control industrial processes are not acceptable. Outages often must be planned and scheduled days or weeks in advance. Exhaustive pre-deployment testing is essential to ensure high availability for the ICS. Risk management requirements. In a typical IT system, data confidentiality and integrity are typically the primary concerns. For an ICS, human safety and fault tolerance to prevent loss of life or endangerment of public health or confidence, regulatory compliance, loss of equipment, loss of intellectual property, or loss or damaged products are the primary concerns. System operation. ICS operation systems and control networks are often quite different from IT counterparts, requiring different skill sets, experience, and levels of expertise. Control networks are typically managed by control engineers, not IT personnel. Resource constraints. ICS and their real-time operating systems are often resource-constrained systems that do not include typical contemporary IT security capabilities. Legacy systems are often lacking resource common on modern IT systems. Additional ICS protocols and security considerations are the following. Communications. Communication protocols and media used by ICS environments for field device control and intra-processor communication are typically different from most IT environments and may be proprietary. Change management. Change management is paramount to maintaining the integrity of both IT and control systems. Unpatched software represents one of the greatest vulnerabilities to a system. Software updates on IT systems, including security patches, are typically applied in a timely fashion based on appropriate security policy and procedures. Managed support. Typical IT systems allow for diversified support styles, perhaps supporting disparate but interconnected technology architectures. For ICS, service support is sometimes by a single vendor, which may not have a diversified and interoperable support solution from another vendor. Component lifetime. Typical IT components have a lifetime on the order of 3 to 5 years, with brevity due to the quick evolution of technology. For ICS, where technology has been developed in many cases for very specific use and implementation, the lifetime of the deployed technology is often in the order of 10 to 15 years and sometimes longer. Component location. Most IT components and some ICS are located in business and commercial facilities, physically accessible by local transportation. Remote location may be utilized for backup facilities. Distributed ICS components may be isolated, remote, and require extensive transportation effort to reach. Renewable energy sources include the following. Bioenergy is a form of renewable energy generated when we burn biomass fuel. Biomass fuels come from organic materials such as harvest residues, purpose grown crops, and organic waste from our homes, businesses, and farms. Geothermal energy is the thermal energy in the Earth's crust, which originates from the formation of the planet and from radioactive decay of materials in currently uncertain but possibly roughly equal proportions. Hydropower, also known as water power, is the use of falling or fast running water to produce electricity or to power machines. This is achieved by converting the gravitational potential or kinetic energy of water source to produce power. Hydropower is a method of sustainable energy production. Concentrated solar power systems generate solar power by using mirror or lenses to concentrate a large area of sunlight onto a receiver. Electricity is generated when a concentrated light is converted to heat, which drives heat engine connected to an electrical power generator or powers a thermochemical reaction. Photovoltaics is the conversion of light into electricity using semiconducting materials that exhibit the photovoltaic effect, a phenomenon studied in physics, photochemistry, and electrochemistry. Wind energy or wind power refers to the process of creating electricity using the wind or airflows that occur naturally in the Earth's atmosphere. Modern wind turbines capture kinetic energy from the wind to generate electricity. This slide depicts the energy and information flow in a renewable energy system, in particular the photovoltaic or solar energy system. Electric energy flows from the PV array or solar panels to the inverter, then to either the energy storage equipment or the service panel or sub panel. Electricity flows either to the smart meter or to consumers before moving to the utility grid. Information flows from the smart meter to either the system controls for controlling the generation of electricity or to the utility grid. If additional energy is needed at night or cloudy day, the energy storage will give back some of its stored electricity. The system controls get additional information from the internet, say for weather conditions, to be able to better manage the flow and generation of electricity. This list of vulnerabilities on ICS is not exhaustive. We present herein some of the most important. Inadequate change and configuration management. Mostly configuration changes and patches are not verified for correctness. Inadequate continuity of operations or disaster recovery plan. In this case, emergency response procedures unintentionally omit security controls. Inadequate network segmentation. An example is the OT network is connected to untrusted networks or that network interfaces permit unnecessary traffic flows. Insufficiency trained personnel. Workers are not trained on security policies and procedures. Physical access to devices. Physical devices such as PLCs, sensors, switches, and others are not properly secured. Weak authorization and authentication mechanism on control. This vulnerability on weak authentication process or authorization keys is prevalent on legacy systems. Use of insecure protocols such as Modbus and DNP3. Unfortunately, many ICS and renewable energy systems are operating with these insecure communication protocols. Attacks on industrial control systems may include one or more of the following: IT OT insider. A disgruntled IT or OT operator or technician can easily snoop for privileged password to carry out a malicious attack on ICS system. Ransomware, an inadvertent virus download, or an email phishing can trigger a ransomware attack similar to what happened in the Colonial Pipeline attack. Ukrainian energy attack was perpetrated through phishing by a nation state and shut off power to over 200,000 people for up to 8 hours. Market manipulation. Organized crime syndicate targets vulnerabilities in IT systems to get to the OT systems and manipulate the control equipment to react during high energy or commodity demand. This will, in turn, control the supply of that commodity and manipulate the market. Mobile phone Wi Fi. The attackers would plant a malicious software in smartphone apps and continuously scan for Wi Fi networks and critical infrastructure workplace. The Wi Fi network, if left unprotected, can be compromised at that workplace. Additional attacks are the following: hijack two factor. The sophisticated attacker compromises the two factor authentication mechanism to attack the remote access of the critical infrastructure from the home network of the operator. Industrial Internet of Things pivot. Poorly defended IIoT devices are used as entry point for attack in this case. Malicious outsourcing. The outsourcing of remote support function control system components may be used to compromise an ICS system. Compromised vendor. The poorly defended vendor website may be compromised and could serve tainted patches for control system devices. Compromised remote site. A remote site that is not physically secured could be the source of malicious software that can propagate to the main network. Here are some mitigations to ICS threats and attacks. IT OT Insider. Use network segmentation and fail-safe controls. Ransomware. Use removable media control and a unidirectional gateway. Ukraine Energy. Use multi-factor authentication and email filters. Market manipulation. Use continuous monitoring and input validation. Mobile phone Wi-Fi. Use intrusion detection systems and secure the Wi-Fi networks. Additional mitigation techniques are the following: hijack two-factor. Use unidirectional gateway and disallow remote control. IIoT pivot. Strengthen IIoT security and use segmented network. Malicious outsourcing. Disallow remote control and carefully vet outsourcing vendor. Compromise vendor. Require additional check of vendor site and use virus scanner. Compromise remote site. Physically secure remote site and enforce access control. The increased security risk brought about by renewable energy opens the new trends to cyber threats. These trends are the following: the increased connectivity and insecure connections, the adoption of standardized technologies with known vulnerabilities, the increase in IT OT connectivity, the increased availability of technical information which enable hackers to better understand the renewable energy system architecture, the increased reliance on automation, and the introduction and integration of new energy sources.